Okay, welcome back to chapter 2. So we're going to continue our journey through the textbook and through the field of astronomy. So to get us started, we should talk a little bit about what we actually see when we look up at the sky and some key terms related to that. So when you look up at the sky, what you're seeing is a hemisphere, right? You're seeing half of a sphere, and that's because the ground below you is obscuring the rest of the sky. Okay, so we call that point directly above you. If you look straight up in the sky, we call that the zenith, which actually comes from Arabic, if I remember right. And we'll talk more about that history a little later. And the region around you, the circle, the boundary between the sky and the earth, we call the horizon. And so that horizon is only perfectly flat and circular if you're out at sea, where, hopefully the waves aren't too tall. On land, there tend to be mountains or houses or random other things in the way, but it'll be roughly circular. So if you lie on your back and observe the stars, you'll see the zenith above you, and if you watch for a long time, you'll observe that the stars slowly rotate around the sky, and the point that they rotate around will be one of the poles. And since we're in the northern hemisphere, or at least I am, that would be the North Pole. We'll talk more about that a little later. So what does this look like if we zoom out a little bit? Well, you can see here we have a picture of the Earth with a person standing vertically. So they would see everything on the top half of this Earth here. You can see there's a red line, which is the person's horizon, assuming that there are no houses or mountains in the way. And the zenith, in this case, is directly up, the top of the sphere. But the North Pole, if we extend that outward into the sky, then we have what's called the North Celestial Pole, and that's the point that we see the stars rotating around. The stars are not really moving, we're the ones moving, but from our perspective, we feel like we're still and we see the stars as if they were moving. So this celestial sphere, this ball here in the picture, from our perspective, the stars tend to be fixed to it. So they're moving as the Earth rotates, but relative to one another, they stay in the same position. Now, as the Earth orbits the Sun, where that position is in the sky will also change as a result of that motion. But if two constellations are next to each other at one moment, they will be next to each other anytime in the future. It's just they might be somewhere else in the sky, or they might be hidden under the horizon from our perspective. Okay, so continuing on, what is our perspective? Well, as the Earth rotates, new stars emerge. Basically, if any star is below the horizon, we won't be able to see it. So the extreme case of this is that in the northern hemisphere, there are some stars and constellations that we'll just never see. They're always below the horizon. If we look back at this picture, any stars that are near the South Pole, the bottom left in this picture, as they rotate around, let me grab my annotator so I can draw in here. So here's our South Pole. Any star down here is going to rotate around, but it will never cross our horizon. So we won't see it from this position in the northern hemisphere. Okay. And so you can see in this picture we have the Big Dipper, the Little Dipper, and Cassiopeia. And the Little Dipper, of course, has the North Star Polaris within it. So these three constellations are always going to be next to each other. It's just that sometimes they will be rotated. So, as the Earth spins on its axis. And if we were in the southern hemisphere, we wouldn't be able to see any of them because they would be below our horizon. The Earth's just in the way. Okay, so let's look at a few more diagrams just to help us see this. So what if we're standing at the North Pole what do we see? Well, our zenith then would be the North Pole, and so we would see all of the stars in the top half of the celestial sphere. As the Earth rotates, we would see them move around in circles, orbiting the apparently orbiting the pole. But none of them would be going below or above the horizon. Okay. What about if we're at the equator? So at the equator, you could actually see any star except maybe Polaris. Like any star that's exactly on the pole would be very hard to see. But at the equator, you'll see all the different stars. But throughout the course of the night, they will rise above the horizon and move back down below the horizon. Okay. And so you can see most people, including people who live in large parts of Asia and Europe and North America, live neither on the pole or the equator. They live somewhere in between. And so for us, we will see some stars that stay in the sky as they rotate, so stars near the North Pole. And then the rest of the stars, sometimes they'll be above the horizon, sometimes below. And then some stars that are near the South Pole, we will just never see. Okay. We call that extension of the North and South Pole, we call those the celestial poles. We can also imagine extending the equator out sideways, and that's the celestial equator. And so, like I said, the stars, if we watch throughout the course of a night, we'll see them rotate around. This photograph is what happens when we allow for a long exposure. So we let light into our camera over the course of a long period. It tends to kind of blur anything that's moving. And what we see is that blur is creating these circular patterns. So you can immediately see, okay, I can't tell which one it is, but either the North or the South Pole is in the center of these circles. That's one of the celestial poles. Okay, so that's how the normal stars work. Now, the sun is not a normal star because, of course, it's very close, relatively speaking, and we're orbiting it. And so the sun does something a little bit funny in the sky. Basically, what's happening is the Earth is tilted at an angle relative to the plane that it's orbiting the sun within. And we'll see some more diagrams of this a little later. But the result is that during the summer, the sun stays in the sky for a long time. Basically, it's almost right overhead, and we can see that's this red curve. This is the path of the sun somewhere in the northern hemisphere on June 21st, so near the solstice. And then as we get closer to winter, we get farther and farther. The sun moves toward the horizon. Eventually, on December 21st, so somewhere near the winter solstice, the sun follows this green trajectory. It's not in the sky very long. We all know that happens because we know the days are shorter in winter. The sun is at a different position in the sky. Okay. Now, this is a little bit different than some of the other stars that we'll see, so we'll have to talk about that as we progress through the course. But you should remember the sun is special. Now, the path that the sun takes is known as the ecliptic. So the ecliptic is a vocab word we have to get comfortable with, and we'll see what this looks like when we map it on the celestial sphere in a moment. But this is what causes the day to be longer in the summer and shorter in the winter. In the northern hemisphere, this has a particular association with the month, right? So June is summer. Turns out it's flipped in the southern hemisphere. We'll talk about more later. And so this looks confusing when we see these different shapes. But if we, okay, this is not the picture. This is the picture that I wanted. But if we map it into the sky, so again, our zenith is upward in this picture. And you can see that the sun is creating this red line. So here in this picture, it looks like our horizon, but that's just a coincidence. basically the sun here is following the ecliptic path, and the celestial equator is this dash circle line. And so when it's December, you see the sun will be over here on the left. That will be its position in the celestial sphere. So it'll be near some constellations, not others. And by the time it's June, it'll be over here on the right in the celestial sphere. So this is the picture I want you to hold in your mind. Most stars stay fixed to the celestial sphere. They are all in the same positions relative to each other. Whenever we see the Big Dipper, it's always near the Little Dipper. We might see it rotated a little bit, we might see it from a different angle, but those two will always be near each other. Things like the sun are the exception. The sun moves around within the celestial sphere to different positions, okay? And this is why we have seasons. We're going to talk about more later, but the seasons are a result of the fact that this ecliptic plane where the sun travels is at an angle relative to the celestial equator. Another way that you might have heard people say this is the seasons are caused by the tilt of the Earth. What do we mean by tilt? This angle between the Earth's equator and the path of the sun, the ecliptic. So sometimes the sun is shining directly on us. That's the summer. It's more directly ahead. And sometimes it's shining more of an angle. That's during the winter. Okay. So as the sun travels through the celestial sphere, what's actually happening? Well, we now know the Earth is the one really traveling, the sun's staying still, but we're seeing the sun from a different angle, and so it appears to be in a different spot in the celestial sphere in the sky. And if you're into astrology, which we're going to talk more about later, you maybe already know how this works. Basically, at each time of the year, there is a constellation that the sun is next to. So these constellations stay in the same relative position to one another. So Cancer and Gemini are always next to each other in the night sky. Sometimes we're able to see them, sometimes we can't. Sometimes they might be rotated from our perspective, but they'll always be next to each other. However, the sun is only near Cancer during roughly the month August. And so at other times of the month, the sun will be near other constellations in the sky. And basically the ecliptic passes through all of the constellations listed here. Those are the zodiac constellations. And that's how we determine someone's zodiac sign, is where does the sun appear to be in the sky. Now, of course, we cannot see the constellation that the sun is next to because it would be visible during the daytime, which we can't see other stars then because the sun's just too bright. But we know the path the sun takes, and we know where it's going to be. So if we can see Leo and Gemini near the sun, then we know that the sun has to be at Cancer. Okay. So this is all connected then to these paths that the sun takes at different times of the year. It just depends on where the sun is at in the celestial sphere, which corresponds to these zodiac constellations. Pretty nifty. Okay, so like I've been saying, we have this celestial sphere, which is where all of the fixed stars, all of the normal constellations are sort of glued to, we can imagine. So you can see here Andromeda and Cassiopeia are always next to each other in the sky. Now, at different times of day or different times of year, they are going to be in different places, like from our perspective, but the sphere always looks the same. It just gets rotated around, basically. Okay, enough on this, but if you can't visualize it, I'm going to give you some more resources, and you can feel free to ask some more questions to try to imagine what this looks like. It's really important. However, in addition to the sun, there are some other bright spots in the sky that seem to move around. Sometimes they'll be near one constellation, sometimes they'll be near another constellation. In Greece, they had a name for these things, which was wandering stars. They look just like stars with our eyes, but they seem to move around. We know today that these are planets. So the planets, because they're also very close to us and their position, our view of them changes as we orbit around, they seem to be at different spots in the sky relative to the constellations. Now, the solar system is relatively flat, just like how our galaxy is relatively flat, and we are going to talk about why that is. It's not a coincidence. But what that means is that all of the planets are pretty close to this ecliptic plane. So this red curve here, where the sun goes around, all the planets are going to be pretty close to this line as well. So they all go roughly through the zodiac constellations too. This is why you might hear people talk about, like, well, if if Venus is in Pisces or something, maybe there's some meaning associated with that. And in addition, the moon is also pretty close to the ecliptic. So all of the kind of moving objects in the sky, other than comets and asteroids, are going to be close to that ecliptic plane where the sun is moving. Okay. So what are constellations? I guess we should have mentioned this earlier maybe, but basically, if we go somewhere really dark and we just have our eyes, we can see roughly 3,000 stars in the sky at any given time. Now, of course, if you're at a different spot, so if you're in the southern hemisphere, you're going to see different stars because you'll see ones that would have been blocked by the horizon from the north. But regardless, you can see about 3,000 with your eyes. And so to help us remember these, and especially in ancient times when we use constellations more frequently for things like navigation, we can have groups of stars that we give names to, and we can tell stories about them, and we can try to see them as little stick figures or so on. So for example, we have the 3 stars here in a line. This is Orion's belt. So Orion is a very famous warrior constellation in Greek mythology. And most every civilization had some set of constellations of their own. But today we have the 88 sort of standard constellations that we think about in the sky, most of which come from the Greeks. And then the ones in the southern hemisphere, a lot of them come from random European explorers who went down there to map star charts for themselves. Okay. I will not expect you to memorize all of the constellations for this class, but it's good to know a few of them, especially the zodiac ones come up a lot, and some of the ones that are more commonly visible in the northern hemisphere, we're going to occasionally reference just as sort of landmarks, remember, because the celestial sphere stays pretty constant. So we can use these constellations as landmarks in the sky, even though they'll appear at different places. From our perspective, relative to each other, they're going to stay stuck on that sphere. Okay, so astronomy, like I said in the first lecture, it's one of the oldest sciences. We've all looked up at the sky at some point in our lives, and so did our ancestors. And so at least 3,000 years ago, and probably much, much earlier, humans already had a pretty accurate sense of astronomy and had found some very useful patterns in the stars. And so the first thing this was used for, from our understanding, is developing calendars. So once we, as a species, discovered agriculture, so we started planting crops, we wanted to do it at standard times. No one had watches or ways to keep track of time, with technology devices. So we use the stars, right? We already know from what we talked about that depending on what constellation the sun is in, that tells us roughly what month it is. So from that alone, you can get a pretty good sense of when you should plant your beans and when you should harvest them. The Egyptians used this to figure out when the Nile River would flood, which happened pretty regularly every year. Chinese astronomers, really famous for measuring solar activity, solar flares, as well as a lot of supernova data that we still use today, even though it's thousands of years old. Mayans had sophisticated calendars. The Polynesians, which I have this book here if you're interested in learning more about how they did it, but the Polynesian people were able to navigate all across the Pacific, primarily using the stars to tell which direction they were going and to help identify if they were near any known islands that they'd already discovered. So astronomy, it's really an ancient art. of course, a lot of astronomy in the West, and for good reason, traces its roots back to ancient Greece. So ancient Greece was a society formed from a bunch of city-states that they were all constantly in some sort of conflict with each other and with Persia and a bunch of other places. And as a result, they had the right social and material conditions to really advance technologically very quickly and pretty far for their time. So there were a lot of really big strides taken in our astronomical knowledge by Greek astronomers. So what are some of the things they discovered? Well, they figured out that the Earth had to be round. Not only that, but we'll talk about that they even measured the radius pretty accurately. They understood not only the lunar phases, but why they happened, which we'll also talk about in this class. They were able to roughly predict eclipses, which is quite challenging to do, and they still didn't quite understand how to do it, mostly because they didn't have enough data. Some Greeks even proposed the sun as the center of the solar system, which was really wild for the time, but as we know, turned out to be true. Although most Greek astronomers didn't think that was true because of something called parallax, which we're going to learn more about later. And Archimedes, the famous Greek scholar, not only did he realize through his mentor that the sun was at the center of the solar system, but he even used parallax to roughly measure the size of the universe, which is the size to the nearest stars, because he thought the celestial sphere was roughly where all the stars were, although in reality, right, they're spread out throughout the universe. And he calculated how many grains of sand it would take to fill in that volume, and was able to get a pretty reasonable number for the time, which is kind of crazy. So anyways, they made a lot of important discoveries and sort of set the foundations for Western astronomy to come. And all this knowledge was actually traded around in all of the old world. So the Greeks learned from Chinese and Indian and Arab astronomers, and vice versa. There was a lot of interconnection that we kind of take for granted these days. So I alluded to it already, but how did they do it? The ancient Greeks did measure the radius of the Earth. So not only did they realize it was pretty spherical, but they measured it. So a famous Greek whose name I will butcher, but Eratosthenes, he knew that there were two cities in Egypt, so Alexandria and Syene, and he knew that at a certain time on a certain day that the well in Syene, light was able to get all the way to the bottom. So basically the sun was directly overhead. And his idea was that at the same time and day, in another city pretty far away, Alexandria, he would measure the angle of a shadow from a column. So he would measure how long the shadow was, and he knew how tall the column was. They could do trigonometry back then, so he was able to get that angle. And once he had that angle he found was 7 degrees. So the shadow in Alexandria was pretty small. It was a pretty short shadow, only 7-degree triangle. And he knew that 70 degrees is 1/50th of a circle. There are 360 degrees in a circle. So 1/50th of that is 7 degrees. And so therefore, he was able to argue correctly that those two cities were 1/50th of the circumference of Earth apart. And so since he knew how far apart those two cities were, they were 5,000 stadia, which is an archaic unit of distance. He was able to measure the Earth's circumference and thus its radius, right, 2 pi r. And as far as we can tell, depending on which definition of stadia he used, his measurement was only about 1% off. So he was very, very precisely able to measure the radius of the Earth, which is kind of crazy. So for a few thousand years ago, right? Okay, what else were the Greeks able to precisely measure? Well, Hipparchus, who is considered kind of one of the Greek founders of astronomy, he did a lot of really important work. First of all, he organized all the stars that were visible by the eye from Greece by brightness. So we still use his system today, which we will learn about more later, but he called the brightest stars the first magnitude of brightness, and then a little bit dimmer, he called those the second magnitude, and a little dimmer the third magnitude. So the bigger the magnitude, actually the dimmer the star in his system, which is a little confusing. We still use it today, and that's because all of this ancient data, we have to still use it in astronomy because a lot of things are very slow in astronomy. And so we need all of this really old data in order to accurately find the patterns, which is big part of our goal. Hipparchus also noticed that the celestial sphere, the orientation of it relative to Earth actually changed. So where the north celestial pole points, so we now say that it points at Polaris. But what Hipparchus noticed is that when he looked at even older records of astronomy from his, great-grandfather, whoever, that the north celestial pole was at a little bit of a different spot. So some people would just think, oh, the data's wrong. There's a problem here. Sorry, hold on one second. Okay, so some people would just think that the data was wrong, their grandfather made a mistake, but not Hipparchus. He realized that this was actually similar to if you spin a top. If you've ever played with some toy tops, they start to wobble. So as the top spins around, it kind of wobbles a little bit on its axis. In physics, we call this precession. And so it turns out the Earth is precessing. Now, it's doing it very, very slowly. So it'll take about 14,000 years for the North Star to change from the current one, Polaris, into another one, Vega, that's nearby. But it is something that if you're doing precision astronomy, you have to keep track of very carefully because it changes our perspective, right? The celestial sphere is not changing, but how we orient relative to it slowly is changing over the course of hundreds or thousands of years. Okay. So the stars, though, those are the easy things to deal with. The tricky part is the planetary motion. And so people all over the world notice this idea that the planets move in a really weird way. And what I want you to see here as we go around the circle. So here we're going to go around the circle A, B, C, D, E. And what I want you to notice, so let's say that this is Earth, that's the blue dots here, and the yellow dots, maybe that is Mars, a planet a little farther away. So when we're at point A, we see Mars at spot A over here on the right. At point B, we see it at point B. But look at what happens. As we orbit around the sun, it appears like the planet Mars is going backwards at point C. Even though, see how it actually moved forward, A, B, C, D, E, it's moving in the right way. But from our perspective, because we're orbiting a little bit faster as we get closer to the sun, we see it go forward and then back and then forward again. Okay, we see this strange backwards motion. And if you think back to ancient Greece, they didn't, for the most part, they didn't realize that the sun was the center of the solar system. So this was a really strange phenomenon. They had a lot of trouble explaining. And we're going to talk about some of the methods they used in a moment. And so to explain this, it took a few hundred more years until Ptolemy, who was a Greco-Roman astronomer who lived in Egypt, which was kind of colonized at the time by the Greek society. And so he was able to summarize all of Western astronomy that he had access to. That was his first big project. And then after he had all this data together and collected, he was able to make his own model for how the solar system worked. And so what he imagined was that Earth wasn't quite at the center, but it was very close to the center of the solar system. And that all of these other objects, not only were they orbiting around the center, but they were also orbiting around that point on their orbit. So if you can imagine this, it's going in a circle as it moves in a circle. And when something does this motion, it can explain this forward and back looking thing in the sky that we see here. So if this were what was happening, it would explain it. And Ptolemy was actually able to do this with enough precision that he could explain and predict the motion of the planet. So in a way, the Ptolemaic model worked. It allowed for prediction, but in another way, it failed because it wasn't actually what was happening. It wasn't physically real. And it was also really complicated. You had to have all of these little mini orbits, which we call epicycles, that each had their own properties that had to be measured. And when you were doing calculations, it was very, very challenging to keep track of all of them to figure out where something would be in the night sky. So you can imagine it was, quite nice to have this model, but it was also a bit of a curse. You had to get a lot of really smart people together in order to actually do anything with it. And so, okay, we're going to put a pin in that. So we're going to put a pin in Ptolemy for now. We're going to talk more about the development of astronomy as a science a little bit later. But I do want to spend some time talking about astrology because it is relevant to astronomy. A lot of ancient astronomers were astrologists. They thought that we could predict the future by looking at the sky, and honestly, for good reason, in a sense, right? The sky is a very beautiful and magical looking thing, and they'd already figured out that they could predict whether it was going to be hotter or colder based on the sky. That's just the seasons. So why not other things? Why not being able to predict when you're going to get married, or if there's going to be a drought or a war, all sorts of things? They would look to the sky and try to find some pattern. And humans are very good at finding patterns even when they're not there. And so they found a lot of things to keep track of. It also helped fund astronomy in ancient times. So every king or emperor wanted some astronomers because they thought they could predict the future, right? Why wouldn't you want some of these people, these really smart people doing a lot of math and apparently helping you figure out what you should be doing? Okay. So the most common form of Western astrology is based on the horoscope, which are those constellations, those 12 constellations that are arranged around the ecliptic plane. So the ones that the sun passes through as it moves through the celestial sphere. And so each one corresponds roughly to a month. Now, because of the precession that we talked about, the signs have actually shifted a little bit over the last 2,000 years, roughly, since they were standardized. And so they're off by about one sign today. So if you, I forget the order they're off in, but I think if you think you're an Aquarius, by modern analysis, you would maybe actually be a Pisces or something like this. Of course, based on your sun sign. You can also ask where other wandering objects, so the moon and all the planets, where those are relative to these constellations. They're also, because the solar system is pretty flat, they also are mostly aligned with this ecliptic plane, so they can be positioned in reference to these same constellations. And putting all this together, you start to get sort of the foundations of astrology as a method. So astrology is still popular today for predicting things, despite the fact that there have been multiple scientific studies that haven't been able to find any predictive power. But, people really enjoy patterns. They enjoy, trying to guess at the future. And also, sometimes we can use astrology just as an excuse to do things that we maybe wanted to do anyways. Like if you say, oh, my astrology predicts that I should take this job, and that was the job I wanted to take already. In addition to the fun that you can have with it on its own, it can also be a good intro to astronomy. It can help you understand a few constellations, what order they're in, and we know they're around the ecliptic plane. And I encourage you to try to find these constellations in the night sky and try to keep track of them. It's a really good exercise. And like I said, the planets and all the other kind of moving around objects on the celestial sphere will also tend to be amongst them. So if you use one of those astronomy phone apps, you can see all these zodiac constellations along with a lot of other interesting things like the planets in the same place. Okay, so astronomy as a science, like I said, in the West, we mostly attribute that development to ancient Greece, but there was a lot of interconnectedness with China, with India, with parts of Africa, and of course, in the Americas, there was also an independent astronomical tradition from the Olmec and the Mayan and the Aztec and the Incan, all of these great civilizations, but also a lot of smaller ones that were interconnected. But modern astronomy, in many ways, grew out of this period after the fall of the Roman Empire, where Europe entered the Dark Ages, where not much new research was being done. But the Arab and Asian societies continued on their work. So they had access to the ancient Greek books, they had translated them into their own languages, and they didn't just sit there and read them, they did things with them. So here I've listed a bunch of Arab astronomers whose names I will also fail to pronounce well, but Abd al-Rahman was able to map a lot of galaxies across the sky, which look a little bit different than normal stars. So even though they weren't quite sure at the time what they were able to note that these were some unique and interesting objects, and we still use their observations today. Al-Ilya and Al-Astrabia developed this really important tool known as the astrolabe. And so there's a picture of one here, and there are also some pictures of them in this painting in the top here. And basically what it is it allows you to get the exact position of a star in the sky, so we can actually keep track of them instead of just drawing pictures. We can keep track of them numerically. And so what it does is it lets you measure the angle. You see that star is at an angle, that's this dashed line, from the horizon. So we can tell how high above the horizon a star is. And with that, we can start to map stars' positions. The Arab astronomers also really expanded on the Ptolemaic system, so the epicycle stuff. They made new measurements, they added epicycles within the epicycles, and they were able to get really precise predictions of the planetary positions over time by continuing to develop these methods. Okay, so then after this period, this Dark Age period in Europe, as a lot of things started to happen, Europe entered what's known as the Enlightenment. So this isn't a history, you could teach a whole semester course on just the Enlightenment, but basically, whenever a society is fragmented in city-states, like we saw in Greece and also in Europe, if it has enough time for this to percolate and different mercantile and productive forces come along, then it can lead to technological development. And so Europe saw a lot of this, not just technology and science, but also technology in the sense of corporations and double entry bookkeeping, all sorts of really interesting things. And through the process of this technological development, Europe also came back in contact with a lot of different societies, including the Americas, right? Through Columbus and the conquistadors, all these people. And so they learned a lot of things from this contact, from contact with the Arabs during the Crusades, from trade with all different parts of the world, and also through conquest and genocide and a lot of really bad things. But basically in this process, Europe became the center again of astronomy, and Northern Europe for the first time became the center of astronomical development as a science. And one of the first people to really make a new breakthrough as part of this was Copernicus. So Copernicus was working in the late 1400s, early 1500s, and for no other real reason than he just liked that it was much simpler, he proposed that the sun was at the center of the solar system. This was a really radical proposition. It had been a long time since ancient Greece where people freely argued about this. So most of the world at that time thought that Earth was the center of the solar system. So Copernicus really provided a lot of evidence and framework that this was not the case. Mostly, though, this evidence wasn't so much scientific as it was philosophical and mathematical. So he was able to predict the positions of the planets much more easily. So it was kind of like a shortcut in the calculations. And he was also able to do it much more elegantly, which is something that most people really appreciated. But it took almost 100 years for this view to become common and popular. And so we call this view of Copernicus heliocentrism. It's the idea that the sun is at the center of the solar system. So now you can buy it as a Lego set like this. And like I said, it explained the data much better in the sense that it was much simpler, easier to calculate where the planets would be. But it was a really big leap. And I want to highlight that it took a lot of development from many societies that Europe was in contact with, not only from some Greeks who had really developed astronomy, but from the Arab scholars who realized that Earth was rotating, which was a really important part of this framework, and Indian astronomers who had made a lot of progress with some ideas about relative motion of the planets, like they had started to lay the groundwork, I should say, for this development of heliocentrism. But like I said, it took about 100 years for this view to become really popular, and the person who's responsible for popularizing it is none other than Galileo Galilei. And so Galileo, whose bust and picture are right here on the slide, was not only an astronomer, but really he was a physicist. So he wanted to understand the laws of nature, and he was one of the first people in Europe to use this scientific process, actually doing experiments and testing things to definitively answer whether or not things worked one way or another. And one of the causes that he applied himself to was this debate about heliocentrism. And so what did Galileo do? Well, one of the things that he did was he was able to gather data on the phases of Venus. So basically, as we look at Venus, if you look at it just with your eyes, it looks like any other star, even though it's actually a planet, reflecting light rather than emitting it. But if you look at it very carefully, you can actually see that it has phases just like the phases of the moon. And the only good way to explain this is if the sun, not the Earth, is at the center of the solar system. So we can see in this diagram that the way we get phases on Venus is as it orbits the sun, the Earth sees a different portion of the planet. And so, for example, when Venus is on the opposite side of the sun from Earth, it looks very bright, almost the entire face is lit up. Whereas when Venus is on the same side of the sun as Earth, it's much dimmer. More of it is in shadow. And so this was kind of the definitive proof that the heliocentric model was correct. Of course, the Catholic Church had some problems with this. Galileo ended up in house arrest for a lot of his life because he refused to recant this, treasonous belief that the sun was at the center of the solar system. But through his experiment and his data collection, now we all pretty much agree, all scientists at least agree that this is the only way to make sense of planetary motion, is with heliocentrism. So in addition to the phases of Venus, Galileo also measured a bunch of other things that are relevant to astronomy. So he noticed that there are dark spots on the sun. He found moons around Jupiter. So this was a really crazy observation that to us maybe doesn't sound very interesting. But at the time, people thought of space as a very perfect place. So when Galileo found that the sun had these weird blemishes, these weird imperfections, that Jupiter wasn't just a perfect shining object, that it actually had moons, like how the Earth has moons, he was able to make detailed sketches of our moon, showing that it had mountains and valleys on it. And he was also able to look into that milky stretch on the sky, the Milky Way, and actually tell that it was made of stars. That it was, they didn't have the word, this idea of a galaxy yet quite fully, but that it was a huge number of more stars that we didn't even know about before. And so you might wonder, how is Galileo able to do all of this? Why hadn't people done it before him? And it was because he was the person who first realized that we could use a telescope for astronomy. So telescopes were actually invented by the Dutch, and they first started using them for the military. You can imagine if you're an army and you want to count how many troops the other people have sent, maybe, you can do it much earlier on, when they're much farther away, if you have something with a little magnification, like a telescope. Now, telescopes were hard to invent. It took until the 1600s because you have to make a very clear glass for the lens, and you have to grind it with some sandpaper basically to get it to just the right shape that you can actually magnify an image without making it impossible to see. But as soon as Galileo heard about this invention, he hadn't even seen one, he just heard that it existed, he was able to build his own and make it about 10 times better. So going from 3 times to 30 times magnification. And he realized immediately that this would be a wonderful tool for astronomy, because in astronomy, there are lots of objects that are very faint, that are very hard to see. And this includes all the things we just talked about. And Galileo was then able to actually look at them. Before him, no one could make them out. It was just too challenging. And so ever since, astronomers have used the telescope as our favorite tool. It is our window to the universe because it allows us to see objects that would normally be invisible. Okay, so with that, I will end this video, but like I said, keep on watching. We're going to watch through chapter 4 for this week, so I'll leave you to watch the next one.